Professor Blanchet. This is his second visit to LUMS, but I think third or fourth visit to Pakistan. And recently he has supervised the PhD thesis in Abdul Salam School of Mathematical Sciences. And the work was on the braid groups and the quantum groups related to what he's going to unfold today. So this is an introductory talk on quantum topology, and welcome Professor Blanchet in this seminar, and welcome every one of you. So over to you, Professor Blanchet.
Okay, thank you so much. So thank you so much for the invitation. Thank you to everybody for coming. So I will try to give you certain ideas on what is quantum topology. And I would say that more or less I started my mathematics in this domain, starting from low-dimensional topology, quite elementary combinatorial tools, and then this more advanced quantum algebra. So let's, the challenge is to try to give you an idea of this. So it's, because it's an introductory talk, maybe it's good to have certain genesis of the domain. And the first date is 1984, where von Jones invented the Jones polynomial of knots and links. So he was at that time preparing his PhD in Geneva. And then the second step for this, so this is low-dimensional topology, and also the construction now is not so much involved. It was really a surprise. I will explain what. And in 1988, we had a contribution by Edward Witten. And what he said at that time is, let's say, interpretation of Jones polynomial in terms of QFT, quantum field theory. Namely, quantum spaces for the punctured sphere. Quantum states on punctured sphere. So this is really the idea that you have from the beginning this interaction between low-dimensional topology and theoretical physics, quantum states. And then Witten conjectured what he called TQFT for topological quantum field theory. And this means this includes three manifold invariant. Okay, and then in 1989, Reshetkin and Tourayev the conjecture is that they're associated with the Jones polynomial. The Jones polynomial extend to invariant of a tree manifold, and moreover, representation of mapping class group, and quantum states associated with surfaces, and action of cobordism on this. I will come again. And then we have the work of Reshetkin Tourayev. So they got a construction of these three manifold invariants. So immediately, they produced part of this conjectured TQFT. And this was based on Drinfeld work on quantum groups. Quantum SL2 in this case. Then it's nice to take this name and put one star here, put a second star here, and put a third star here. And maybe you guess why I put these stars. Because these three people were filled middles in 90. 3 among 4. Connected to the same domain. So the joke was that this year, this was the quantum field middles. Okay? So the main idea from this is that you have a strong connection between low-dimensional topology quantum field theory and quantum algebra. And you have relation between all those in all directions. And it was the starting point of a very active domain, which was called quantum topology. So let's say, then I think the terminology of quantum topology, the terminology came very quick. So this TQFT was the title, the same title of 2 papers in 1989. One by Vitten and the other one by Atiyah, who axiomatized the idea, the TQFT. And I think the terminology quantum topology should be but this is not completely clear who said this first. But I would attribute this to Luke Hoffman, who wrote a paper with this title in 93. And then this term was completely popularized, and there is now a journal called Quantum Topology, which was created in 2010. But here you can find this terminology from early 90s. Okay. So now, what is it about? So I'm more on this side. So I will give you the objects which are here and try to sketch a few things we understand, we can construct, and try to see what they means, what we do with this. So the first is about low-dimensional objects. So the first is classical knots and links. So a knot is just an embedded S1 in the 3 sphere. And this 3 sphere we usually understand as L3 compactified. So we can draw in the space. And so it should be smooth or piecewise linear embedding. And we look this up to isotopy. So we are topologists and we are allowed to move everything in the space. We do not matter metric, or so on. It's topology. So then, because it's in FR3, we can draw. So we have diagrams. And these diagrams, we take a generic projection. And we get a regular immersed curve. So generic means maybe U0 is not in good position for the projection. It could be completely vertical, but just move it a little bit, and U shadow will be an immersed curve. And then we can draw many examples. Plus over under information at crossing. Piecewise linear. If you take continuous, then this is not good because you have an example of wide knots, and we don't like this.
So why do you need isometry?
Isotopy, up to isotopy, because you are allowed to move. Okay, thank you. I think when we start with knot theory, we usually use this example, which is called a trefoil. But there is another trefoil, which would be done this way. So this one will be the right, and this one will be the left. Trefoil. And already there could be a topologist question, are they equivalent or not? Can you prove that they are not equivalent? So we remember this question. So we have also maybe this one. Sorry, it should be like this, which is a figure 8. And we like also to do links. So for links, you put several copies. Okay. When you do links, you will have a bunch of M copies of S1. And then an example of a link can be like this. This will be the white-head link. Okay, whatever. Sorry. And then it goes like this and come back like this. So here you have one trivial component and another one which goes through. Okay. You have a two-component link. You have a most stupid one, which is just this one. I take, no, when I take this, I mean a disjoint union of S1. I'm embedding a disjoint union of S1. Okay. And then question is, so this is quite elementary. You can start very quickly to play with this. But in fact, this diagrammatics contains algebraic structure, and this is a key point that quantum algebra is realized in these algebraic structures. So here, the important point is that you can construct invariants with this diagrammatic, because you have this Reidemeister theorem, which is that the equivalence relation on diagrams describing links is generated by three relations. First one is introduce a curl. Second one, you remove two crossing like this. So I'm just drawing part of the diagram. Everything keep the same on both sides. Or these are free. Sorry. So you just push one strand over a crossing. So this means that if you are clever, any function on diagrams which is compatible with this relation will give you a link invariant. So it's links up to isotopy are nothing but equivalence classes of diagrams. So this is very convenient. Thank you. Okay, then, so this is quite well known, but you can go further with three manifolds. So you know about surfaces. Here, my three manifold will be compact and oriented. And we already had the example of the three sphere. So compactified space, but maybe you did not work a lot with this, but you have many. Of course, you can take product S2 times S1, but if you know a bit of geometry, you also have the projective space RP3, the space of lines in R4. It happens that this guy is homeomorphic to the group SO3, which is a three manifold. Probably you know better. You can, of course, put the torus. Okay. For the moment, I did not connect with diagram, but I will connect with diagram. And I pretend that I can depict three manifolds. How does this work? So this is the notion of surgery. You don't need to go to a hospital to have a surgery. We are doing this. So let's take G. So it will not be a knot, it will be a thick knot. So then means that I take a torus which I embed in S3. And then I will build Mg, which is S3 minus G of the interior of this torus. So this manifold has boundary identified with S1 times S1. So you took here your thing, and you secant a bit, and you take a pair of scissors, and you remove the interior of this. Okay? Sorry? This is a disk. Okay, this is a disk D2 in the unit disk in C or in R2. Unit disk. Okay, so you see, I mean, a D2 times S1 is something that you draw like this, but it includes the interior. Okay. This you can see for the moment.
This is a kind of a generalization of the concept of links.
Yes, yes. Yes, so here when you do links, you think infinitely thin links, and here I will say thick links or thick knot. And what I can do is union S1 times D2. So, and I glue over G restricted to S1 times S1. And if I want to be careful with orientation, I put a minus here, meaning that I take the S1 times D2 with the opposite of the product orientation. Yes?
I was just curious, when you are doing the D2 cross S1, so is there any change in the property pattern? Because
is there any
change topologically that can happen in the theory of links? Because topologically they are the same, so it can become like a very straight line.
Yeah, but I mean, let's give a few examples. You will see.
The second particular question can be whether the smoothness will preserve.
You have no trouble with the smoothness in dimension 3.
In dimension 3.
Because it's a result of Moïse here that every topological tree manifold admit a smooth structure, and if two manifolds are homeomorphism, then the smooth structure will be diffeomorphic. It's not like in dimension 4. It's much. We are still. It's almost like we are in very low dimension, let's say. Okay, so you have no trouble with this. Don't worry. But if you want to be careful, say that when you do this gluing trick, let's say, so I will answer your picture, your thing. This is a certain manifold. And I cut, but in fact, if I want, here I have a color. Any manifold with boundary, compact manifold will have a color. And if you are in the smooth category, this color is very easy to build. And then, if you glue this with color and this with color, you have natural smooth structure on the gluing. It's not only glue on a surface. You glue so that the neighborhood of the glued surface is a cylinder, and it has a nice smooth structure. So if you are careful enough to work with colors, then you stay in the category of smooth manifold, and there is no question. You can be careful enough. Okay. So here, I wanted to say, the picture, since that you have U naught, so you remove. Here this is empty. And the important point is that you remember where is the longitude. which is G of 1 times S1. In fact, this longitude will be a parallel copy of the core of the knot. We say a framing. And this is enough to know this longitude to know the embedding up to isotopy. Yes? In the classical case, you mean, why would we want this projection? We have enough. We have that. Yeah, but we go first to R3. So there is a result that of equivalence of equivalence. If you can always go to R3 included in S3. Sometimes you need compact, but the classification of isotopy in R3 or S3 is the same. So you can work with knot in R3 and projection. This is true that when you do diagrams, it's correct that you have to be careful if you put diagram in the plane or diagram in the compactified plane.
Because right was to move, everything was, I think, in S2.
It's equivalent. Yeah. Yes, there is a small subtlety here. This is correct. Yeah. There is a small subtlety. But what I mean here is that I put another S1 times D2. And now it happens that the longitude of D2 times S1 becomes the meridian here. And this meridian is identified with the previous longitude. And so if you take example, so then this means that provided, so okay, we have framed diagrams. And the only difference, let's say, the pink was the longitude, but because you consider D2 times S1 or S1 times D2, when you do this, you glue the meridian here with the previous longitude. This comes from the parametrization of S1 times S1. This is the point. Okay? So when you do frame diagrams, you change the R1 by another relation. This means that if you are sick, this is not trivial. So then, means that you do this. Sorry, the other. If you put one curl like this and the reverse, you have nothing. Or here the same. So provided you replace this R1 by modified, a frame version, so we have diagrams with frame Reinmeister theorem. Meaning that, a priori, we have a way, so it's a point, it's not easy. So theorem, I think this theorem is usually attributed to licorice, but it should be also attributed to Orly, saying that all compact-oriented tree manifolds arise in this way, using links. No. So you have No. It's much more difficult. But we are really pleased to have invariants. And also, this is not only that we are interested in three-manifold invariants, this is also the fact that working with this, we get nice structures which are strongly connected with this QFT. So we have all other motivation. So using frame-int, we get all three-manifold. So again, compact oriented. And moreover, so the point is that we know the relation. And this is a theorem of Kirby. So the relation on framed diagrams describing three-manifold up to DFO or Ormeo is generated by Riemann-Maxter moves, framed Riemann-Maxter moves, plus K1. So K1 will take a diagram. So you take a diagram, and you can go to a D and a small things, or to D and a small things in the other direction. Sorry, I should have put example before, but I finish. K2, you take a diagram where you have two different components. And you slide. Take this, and you take this, and you go along, and come back. So this one is sliding. Okay, I'm sorry. I should have done example before. I'm sorry, I'm coming back to the example. I will draw three manifolds. So first is, of course, empty is a sphere. But this guy recovers S3. It's not easy to see. I will give you a list, and I will not explain so much because it would need time. This guy, this is probably the only one you could understand quickly, because this guy, when you remove a D2 times S1, the complement will be an S1 times D2. So this will give you the double of S1 times D2, which is S1 times S2. So this you can see. And here you have to believe me that this guy gives RP3. Maybe it can be also. No, I'm thinking about in the case where this describes G, what is the closed manifold obtained by removing and gluing back. Yeah. Okay, exactly the procedure. Here, you remove and you glue back. At the end, it's closed. Okay, so when I say this is a surgery knots, I mean I will associate to this the manifold which is obtained by taking a thickening of this, removing the interior of the solid torus, and gluing back differently. I'm drawing three manifold, compact three manifolds. It's still orientable because you can check here that my general definition take care about orientation. If you want to be, this one is oriented, say. This one is orientable. You look if the orientation of the boundary match. If they match, that's fine. Okay. Yeah. This is why I put the minus. Okay. Interesting one would be this guy. You see, with Borromean, we are organizing the Olympic Games. And this will give S1 times S1 times S1. And we could generalize and get, if we want, sigma G times S1. But you have many. Okay? So now, the slogan is, if you have, where did I put my sheet here? Yeah, I will be quick on this, but it's important. Of the thickness of the knot, yeah. I'm taking care. It's plugged in the fact that I'm using the frame Redmaster move. If I change, for example, you see that here, the image are the same, but the parallelization is not the same, the parametrization. So this one, here, these are 3 copies of the trivial knot, if you think thin. These are 3 trivial knots, but depending on the longitude, you will get something different. Yeah. Okay. Use as a, yeah, which is the same, sure. You have many. What the Kirby theorem says is that you may have a lot of description of the same tree manifold, but we know that there will be a finite sequence of local move or elementary move going from one diagram to the other diagram. Okay? So you have a tool, a combinatorial tool for constructing invariant of tree manifolds. Take a function of diagrams which satisfy the frame Redmaster move and the Kirby moves. And this will produce an invariant of tree manifold. And in fact, I heard that this Kirby theorem, which was, in the 70s, Kirby said, oh, this will not serve to anything. But we'll see. Okay, before going, I will be quick because I will not have enough time to talk about a bit of quantum. That beyond this, so if you want more about this, we can discuss further. But there are related groups which are braid groups and an easy way to describe braid groups is to take ascending diagram up to R2, R3. For example, this sigma 1 would be an element of B3. This sigma 2 is also an element of B3. Sorry. And if I do this, this is also an element of B3. And you understand, I'm going from the bottom, but this does not important. You see, I'm stacking the diagrams for the composition, for the product. And of course, this guy is the same as, by Redmeister, this is the same as this guy. And so this is, sorry, sigma 1. Sigma 2, sigma 1, sigma 2. So this means that you recover a well-known relation if you work on presentation of symmetric groups. So we can understand the braid group, in some sense, as a quantified version of the symmetric group. Okay? So in fact, this group Bn has generators sigma 1, sigma n minus 1, which were lift of transposition, and relation sigma I plus 1, sigma I equals sigma I plus 1, sigma I plus 1, and sigma j equals sigma j, sigma I, if I and j are more than 2. And this is the presentation. I will be quick, but this is for Imran, that it can be shown that this is some work, that this braid group is a mapping class group of D2 fixing a set of endpoints. And here, I take isotopic classes of map F from D2 to D2, DFO, identity and boundary, and F of points, or set of points, equals set of points. So it's interesting, it's something I will tell further, maybe next week, to understand that the braid group, which has a pictorial description, is also a mapping class group. And the connection is like this. I'll be quick here. If I pick up diffeomorphism like this, I can construct what is called the mapping cylinder, and it will give you a braid. Okay. So I don't want to say more. Okay. No, this is classical braid group. So the classical braid group, it's well known that it is isomorphic to a mapping class group. It's well known. You can find this in the book of Cassel if you want, but it was already. Sorry, it will come back. It's very old stuff. Okay, another group is mapping class groups. So mod of sigma G, this will be genus G orientable surface. And this is class of F, DFO, up to isotopy. This is up to isotopy. These groups are very important for many reasons.
Okay. So we have our topological object and structure. So now we want to talk about invariants. Of knots, links, and braids. So concerning knots, so I will be quick on classical, but I can remind classical. So you have classical. Unfortunately, what you could take each the homology of the complement. With students we are studying homology, so we could try this. Unfortunately, this is not very strong, because this is always, so here K is a knot. This is always Z in dimension 1 and 0, and 0x. So it does not depend on the knot. This is a complementary theorem. So this is not good. But still, you have one classical invariant which is good, but it was known from long time. In fact, you have Alexander polynomial, so 1927. In fact, let's say, I will not define it, but what is very interesting, so you can read the paper. For students, you can read the paper. It's really something very easy to read. It's derived from a presentation of a Z covering space. So S3 minus K, because the homology is Z, the H1 is Z, you can do a Z covering of S3 minus K. And then, okay, the homology here is quite trivial, but the homology of the covering will not be trivial. In some sense, it's a homology with local coefficient. It's easy local coefficient. And this is not trivial. And by the way, this is the only known essentially thing invariant of knots from 27 till 84. And now we got in 84 this theorem of Jones. There exists so we got Phil Miller for this theorem. Yeah.
At level 1, it should not be ZK.
It's a knot. It's a knot. In fact, it's yeah.
In case of S2, then it will be ZK at level 1.
No, it says S3 minus K. It says 3 minus K. It's complement of a knot.
Complement. If I replace S3 with S2, then it will be ZK at level 1?
No. No, no. No, because you separate, so you change the, you are splitting your surface.
Yeah.
Okay, no, that's right. So there exists a unique invariant of oriented links which satisfies polynomial invariant. V of positive crossing, here there is t minus 1, minus t V of negative crossing equal T1 over 2 V of no crossing. If here, this means that the diagram, you have three diagrams which are the same outside the small disk, and you change a bit on the disk. And then you ask that it's trivial. It's one for the trivial. So this is the theorem. It's not difficult to prove, in fact. It was very strong to find this, but it's not very, very difficult to prove. And in fact, the anecdote is that when he found this in Geneva in coffee, he was talking with people, and he said, I found an invariant of naught. And somebody said, no, you found the Alexander polynomial. And the second time he came to the same coffee and said, yeah, I can distinguish left trefoil and right trefoil. And the same guy said, you have to compute again, because he was PhD student, you see, he could not. And then he said the day after, said, yeah, I'm sure. Yeah. Then that was the beginning of the story.
V stand for number of these crossing.
V of this crossing. Sorry. It means that you take any diagram. For example, this guy. You orient. Okay. You select a crossing. Okay. This is a positive crossing like this. So V of this guy will be connected, will be in relation with V of this guy, the other crossing, and no crossing. So recursively, you can compute. It is a polynomial invariant. You see, because you have a variable, so it lives in fact, in the t plus minus 1. This half power will disappear. So it's a Laurent polynomial. Okay. By the way, probably I will not have time to come to this point, but when you have an invariant like Euler characteristic, which is an integer, you like to base this as either dimension of something or the Euler characteristic of some homology. And this works for Euler characteristic. Here, you get an invariant which is a polynomial, Laurent polynomial with an integral coefficient. It could be the graded Euler characteristic of certain deeper invariant. And this invariant was founded in the early 2000s by Misha Kovanov. This is the name is Kovanov homology. And this is one of the perspectives developing now in quantum topology. Okay, so we have Jones. What about quantum? So we will do a small trip in algebra. And so the starting for the trip in algebra is SL2 included in 2 by 2 matrices, which is a traceless subset, and this is known to be a Lie algebra. Operation bracket. You get a Lie algebra, and in fact, this Lie algebra can be presented. In this Lie algebra, you have, for example, H equal 1 minus 1 like this. You have E, you have F, and it's well known that you get generators, and the presentation is obtained with this relation. You can check. This is a computation for first-year student. And then, if we want to go to quantum, we have better immediately take the associative algebra with same presentation. And this is called the universal enveloping algebra. So USL2 is an associative algebra with same presentation. It's no more included in N2 it's very big. The point is we consider a representation. We can study representation. So the irreducible representation, probably you know at least representation of groups. But here, representation of an algebra this is just an algebra homomorphism from this USL2 to an algebra of matrices. This is not very hard. And classification is quite hard, but it's known that there is one recent classification of irreducible. One representation in each dimension. So you get V0, which is C, V1 equals C2, which is the standard representation, the vector representation. You can try to understand V2, but you have, if you take finite dimensional representation, you know all of them. You have also infinite dimensional representation, which can be interesting. Okay, and the point, how do we connect this with invariant? Here we have to talk about the tensor products. So here you take tensor product. If we want to be fancy, we say that USL2 has a Hopf-algebra structure. And for us, the only interest of this is that if VW are representation, then V tensor W is a representation. you know how to do probably a tensor product of representation of a Lie algebra, because you have a co-product which says that the Lie algebra elements are primitive, and that's it. It's not a big deal. This means, and one observation is that the symmetric group Sn acts on V tensor n, any representation, by, this can be any, by intertwiners. So intertwiners are the morphism in the category of representation. So this means that this action, first, the U acts on this tensor product, and we have an action by permutation of factors which intertwine the action of U. And now the slogan for quantum group is, because we think of braid groups as quantization of a symmetric group, so then deform this and quantify. So we go to braid groups. So quantum groups, or quantum SL2. So we take a deformation of USL2. There are two possibilities. Either you introduce, first way, introduce deformation parameter H, or H bar if you like as a Planck constant, if you want to be fancy. Second way, take an integral version of this, and this will be of a C rational function, and here you think that Q equal exponential H, or I pi H if you like to be fancy. And then we get my favorite version of QSL2, we get a presentation. I can, okay. Thank you. It will save a few minutes. So we take UQ SL2 to be generated by T plus minus 1, and you think this is a version of exponential H. Big E, big F, relation KE equals Q2 EK, KF Q minus 2 FK, and bracket EF equals K minus 1 over Q minus Q minus 1. So I need denominators here. So then we can do a representation which are deformation of the previous one. And then we get action of Bn on VQ, say, for the deformation, tensor n, by morphism, by intertwiners. So this will give you a bunch of quantum representation of the braid group. And if you consider duality, you will get a trace. You deduce what will be called the quantum trace. And this quantum trace will give you an invariant of the closure of a braid, which is a link. And so from this we get invariant of links and joints is case VQ equal VQ 1, two-dimensional. Let's say right dimension VQ equal to the vector. But you can do this not only for SL2, but for all these quantum groups. The tools for this is a kind of magic trick, which arises, which is the fact that when we want to do rho v q of this guy, this will come from action of an element of uq times 2. So there is a universal element in the quantum group from the, which give you, it's a really very clever idea of Drinfeld, that this comes for free once you are over with the quantum group. Okay. So again, it's very quick, but the model is a start with Lie algebra SL2. It's universal enveloping algebra, the well-known representation theory, where the symmetry group centralized, and then deform this, and now the centralizer will come from the braid group. Okay, so maybe I should quickly stop. What I could say as a perspective, and we are welcome to discuss this, is that here the point is that this diagrammatic thing provides you a nice algebraic structure, which is the notion of ribbon category. And then the point is that module of an appropriate algebra like quantum group provide ribbon categories. And then to IF came and say, if we take a ribbon category with certain finiteness and extra structure, we will obtain a modular category. We will call this a modular category. And from a modular category, you get 3 manifolds invariants and T50. And now, of course, there are many questions. One question, which I consider a little bit next week, is what is there behind this invariant? There are many conjectures. Essentially, Witten gave a lot. And people are working hard about asymptotics. For 3 manifolds, you need to take the parameter to be a root of unity. And if you take this root of unity to be of bigger and bigger order, you are looking for certain of classical limits, and you expect the volume in the hyperbolic case. This is known in some cases, but still not resolved. And the other question is about applying to this associated group. So it was shown in the early 2000s by Bigelow and Kramer that this representation contains a faithful representation of the classical braid group. Very big result. Classical braid group is linear, and the question for mapping task group is not known. And of course, I sketched the idea of categorification, and I stopped here. Thank you. Why? Just because you have an homomorphism. You see, you have this presentation Bn with the sigma I, the braid, let's say, in short, R3, and for sigma I, sigma j, and commutation, like this. And you know that Sn has the same presentation, R3, commuting, plus Si square equal 1. So you have a natural homomorphism here, which is quotiented by the square relation. Okay, this is in this sense that I think about Bn as a quantization in the sense that when you do back and forth in the symmetric group, you see nothing. But if you do this in the braid group, you remember your history. So your particle remembers the history in some sense. It got some.
So there is some decoration.
Yeah.
Keeping track of that.
Yeah. And then when we do the representation, you see that if we take here, I take the Q parameter, so you can go to Q equal 1, and we'll recover the Sn representation. So I really, and this is really a starting point for out of algebra. So an operator like this, which satisfies the braid relation, is called a Yang-Baxter relation. That was an approach which was refined afterwards. And yeah, it was at that time a very topical question to understand how you can find a Yang-Baxter operator. Okay. Maybe for motivation, I should say that because I said topical, if you want to be topical now, you have to go, there are the topical direction. There is one I mentioned, which is the categorification. And corresponding to this, there is a hope that you can go to four manifold. And also, so next week, we will say, oh, this was quite involved with algebra. We are missing certain interpretation, but if you are clever enough with certain construction from classical algebraic topology, you can recover part of it. So you have this connection, quantum stuff, homological stuff, which is coming again in the topics. Thank you so much.